So this is it's the Newton's Cradle. It's a very popular physics demonstration device, and I have a couple versions of this in my lectures. I think there's a recorded in-person class version. I don't think that's linked from this week's lectures. It'll be next week's lectures as we talk about momentum, and I have a simulated version, but neither of them are really satisfactory because the in-person version, the quality, this is much higher resolution, better quality demonstration than the one in the video next week. And the simulation is always going to have some quirks. And the biggest thing about simulation is, well, it's not the real world. So when the simulation does weird things, you don't really know if it's that particular setup that even in the real world it's gonna be something very interesting, or if what looks interesting is just a simulation glitching out. Because a lot of way things are simulated often involve approximations, and you push those boundaries too far, simulation glitches out. So, anyways, I wanted to try redoing it, so I'm just doing this for the first few minutes to illustrate some things. This is a really nice demo to bring in when we start talking about energy, because the idea of energy ties into really intuitive ideas that people have. Um, and what we define in physics is an attempt at connecting those into those intuitive ideas. So let me just show one thing that illustrates where that intuition comes from. I'm just gonna pull off one of the balls to the side and let it go. It's a fun, mesmerizing demo. And I think as you said, move, you can maybe imagine an ideal version of this. So, this is real world with the air resistance, with the friction, with the whatever. So this whole thing comes to a stop eventually. But it takes long enough time doing that it's possible to imagine an ideal version where I let go of this ball, and this motion that you see in the first two collisions or so, that happens forever. Like, you can imagine that if we were to improve on it, make it perfect, that the first two bounces you saw can go on forever. And that's really where the idea of energy comes from, that there's a bit of some kind of conserved quantity that that persists in things like motion. And and we are going to be working with the mechanical energy in this class, mechanical energy being sum of potential and kinetic energy. And this is an illustration of mechanical energy. When I lift this up, that increases potential energy. That's energy associated, gravitational potential energy is energy associated with the height of this ball. And as it swings down, it gains kinetic energy, and the kinetic energy is transferred all the way to the other side, and this ball goes up with such a speed that it reaches about the same height as the original ball. And that's what someone could look at and say, oh, that's an illustration of conservation of energy. Now, as you look at this, there are some questions that might come up, but let me do a couple of demos first. So you saw the version with the one ball. That's not too surprising, or maybe if it was, well, I think once you say it enough times, then it becomes Monday. So that's the demo with the one ball. Now I want you to think about what will happen if instead of lifting one ball, I lift two balls and let go of them at the same time. Let me give you some time to think about it, and then I'm gonna let go. Fun. So let me try that again. So two balls and let them go. You see how two balls come out? And I think that that's something that I hope raises questions. So it's easy to understand that how if you have two balls raised to some height, then okay, they have twice the energy. But given that twice the energy, why does it have to be that it's two balls coming out with the same speed that they came in? Why couldn't it be that somehow all of the energy goes into one ball and this one ball comes out? Like this one ball goes to this height, like that. I mean, so it's one of those things where, with the conservation of energy alone, if you try to argue that it's not possible for just one ball to come out with all the energy, you don't have enough of a basis for saying conservation of energy somehow prevents that from happening. Conservation of energy allows energy to gather in one object instead of being distributed over multiple objects. And there's a saying in physics. It's most commonly said in particle physics, where there's a context for it that I'm not gonna get into. Um, so I guess the short PT saying is, whatever is not forbidden is mandatory. I mean, referring to if you don't see something happening, so it's somehow forbidden, then the reason you don't see that happening must be because there's a law of physics forbidding it. So, if there was no law of physics forbidding it, then it would have been mandatory in that you would have seen it. It doesn't work in every context. It works in particle physics where there's so many events that if something isn't forbidden, you should see it some of the time, even the very rare events. So here, what I want to propose here is that there is some law of physics forbidding that when I let two balls swing down, there's some law of physics that forbids only one ball from coming out. Some law of physics that dictates that two balls must be coming out. And we are not quite getting that far this week. That law of physics will have to wait until next week to cover that properly. Let me just to wrap this up with a couple demos. So you have seen this with one ball, with two balls. Now I'm going to pull out three balls, and I want you to think about, hey, how many balls are gonna come out when I release three balls at the same time? So, okay, when I release three balls at the same time, how many balls will come out to the right side? Give some time to think, and then let's give it a try. Three balls come out. um, when I do this in class, not everyone, or maybe less than half the class guesses, if they haven't seen it already, less than half the class guesses correctly that three balls will come out. I mean, makes it sense. I mean, in the motion, what it is that the middle ball doesn't really get affected all that much. It's just going. But yeah, three comes in, three goes out. Nothing prevents three balls from going out. Let me try four balls now. Difficult from side. Okay, I got four balls. Let's see. Four ball comes out. I think once you see the version with the three, then the four is not as impressive as it could have been. Now, the last demo, what if I let five balls come in? Yeah, five balls goes out. Yeah, it's very boring. Perhaps the boringest of all. So this is Newton's Cradle, and it's a quite fun demo. Um, I guess it's more of a demo than I don't know if there are interesting physical problems we can solve with it. I guess there are some elastic collision questions you can consider next week. But yeah, so this is the demo.